So, hey everyone, back with another video of what even is a vector. So, vector is the very basic unit of machine learning, not unit, the basic concept of machine learning, since like it is treated as the foundation. Everyone should know what a vector is before started machine learning. So, when most people hear the word vector, they think of this: an arrow, an arrow from school physics. It has a direction, it has a magnitude, done. But in machine learning, a vector can be an image, it can be an audio signal, it can be a customer profile, it can be even a polynomial function that we know of. So, what exactly is a vector? Let's understand this properly. The common intuition of what a vector is, the most familiar idea of a vector is the geometric one, which is it has a direction as well as any magnitude that we call as a vector. So basically an arrow that points somewhere. This is a vector. It has length, it is pointing to a direction, so it's pretty intuitive. Like if I move it 3 unit to my right and 1 unit up, it will somewhat look like 2 3 1 up, this. So from 0 0 it transformed to 3 comma 1, and this movement can be represented as vector, which I just did. So honestly this intuition is useful, but it's incomplete. So what's the big shift? The big shift, let me write it. A vector is not just an arrow. Pretty big statement, right? So this is where ML changes how you think. Mathematically, a vector is even more abstract. A vector is simply an object that follows certain rules and guidelines. So there are two major rules. One is vector can be added, so addition, and second, vector can be scaled. So scaling means multiplication. Multiplication through scalar. Multiplication with scalar. Okay, so addition x1 plus x2, and scaling means lambda x, like that. So if something can be added to another similar object and or multiplied by a number or scalar number and still remain the same type of object, mathematically it will behave as a vector. And this is a much more powerful definition than an arrow. So let me give you a few examples of vectors. First is the most basic example that we all know, which is a geometric vector. Geometric vector. So arrows, yes, definitely. This is a geometric vector. Second is a polynomial vector. Polynomial vector. So if I write x square plus 2x plus 1, it's a vector. Like why it's a vector? Because I can add things in this. So x square plus 3x is another vector. If I add this to this, it will become 2x square plus 5x plus 1, which is again a polynomial, right? So it remains in the same category, hence it's a vector. Now if I even scale it, suppose if I multiply this whole thing by 2, then it becomes 2x square plus 4x plus 2. Again same thing, hence vector. So it can be scaled, it can be added, that's why we are calling it a vector. Third is we have audio vector. So audio vector, like if I talk about audio, what comes to your mind? Waveforms, right? So waveforms are also vectors. So suppose if I make this and if I make this, and if I add them, it will give me I mean, just this line, because they cancel each other, hence they can be added. As well as, suppose if I have to scale them, so it can also be scaled from this to this. Hence audio signals are also waveform. We can also represent audio signals through numbers, so 0. 0.2, 0. 0.5, 0.1. Okay, so since they are numbers, we can add, we can multiply also. How are these numbers and all related to machine learning? So suppose we have image. In image we have pixels. Pixels, we can represent them as a list of numbers. So 0. 0.2, 0. 0.3, 0. 0.5. Okay. Suppose RGB. So this represents a pixel. Then we have audio, in which we have audio samples, which can also be represented as some number. Okay, since we have a waveform, so waveforms, we have amplitude, loudness, and all. So suppose 0.1 for amplitude, 0.3 for loudness, and all that. Then we have customer. Suppose customer, we have age, income, gender. Okay, so these are the attributes of the customer. So we can also indicate them through numbers. And this is why vectors matter in machine learning, because ML model need numbers. So real world things get converted into vector representations, as you just saw. So let's come to n-dimensional real valued space. So this here is called n-dimensional real valued space. We have R1, R2, R3, and all. So in machine learning, we usually think of vectors as ordered list of numbers. Suppose we have this. 1 second. Yeah, 1, 2, 3. So this is in R3 because we have 3 order of numbers, right? We have 3 lists of numbers. So it comes in the 3-dimensional real valued space. So now if you have 100 features for something, then we'll have R100, like that. So if I write vector plus vector equals to vector, and scalar into vector is also vector. So like there's this another elegant idea called closure. Fancy word, simple meaning. If you perform valid vector-vector operations, you stay inside the system. If you perform valid scalar times scalar and vector multiplication, you also stay in the same system. So this is the closure property. Suppose if I give you example, I have 1, 2, and I add 3, 4. I get 4, 6, right? Similarly, if 2, 1, 2, I get 2, 4. This was it. Still vectors. Now let's come to systems of linear equations. So we now know what vector is, right? We know any polynomial can also be a vector. So let's go back and revise what we learned in school mathematics. Most probably in 8th or 9th, I don't remember clearly, but it was about a system of linear equations, mostly two, like two variables. So a1 by e2, b1 by b2, and c1 by c2 we had. Now if all of these are equal, then we had infinite solution. If suppose a1 by a2 is not equal to b1 by b2, we had a unique solution. And if a1 by a2 equals to b1 by b2 but not equal to c1 by c2, then we had no solution. Okay, so we can think, or to give a more intuitive way, we can treat them as lines, because since we have two variables, so infinite solution, one unique solution, and no solution. I mean the overlapping lines, so no solution. Now suppose if we have three variables, then we'll use plane. So we have this Parallel planes, no solution. Intersecting, one second. Intersecting planes, we'll get a single line, which is one solution, and then the overlapping planes, infinite solutions. But now suppose if we have many more variables and many more equations, it will be very difficult to write all of them and solve for each. So we can treat them as vectors and use matrix uh, to portray those equations. Suppose if I have um, a11x1 plus a12x2 till a1nxn equals to b1, a 21x1 plus a22x2 a2nxn equals to b2. Similarly, a m1x1 plus a m2x2 plus a mnxn equals to bm. Suppose I have all these equations. Now to simplify the writing of these equations, I'll use the vector form. So x1, a1, a2 till am plus x2, it will be a11, a21, am1. So yeah, this will be, for x2 it will be a12, a22 till am2 plus x3, a13, a23, am3, yeah, equals to, and write it as b1, b2 till bm, right? And it will be till n. So plus, suppose xn, a1n, a2n till amn. So it will give me this. Now to make it even more simpler, I can write this as a separate matrix for a separate matrix for x. So a11, a12, a13 till a1n, then a21, a31, a41 till am1, and it will go to amn. This will be my one matrix. Now second will be x1, x2, x3 till xn equals to b1, b2, b3 till bm. So this is a, one second, so this will be my a dot x equals to b, and this forms the basis of what we'll study in the matrix part of linear algebra, which I'll be covering in my next video. Now let's move on from all this maths. I mean, this is just the start of it, but okay, for this video let's move on with the maths part. So why this matters for machine learning? This abstraction is insanely useful that we just used or saw, because once everything become vectors, machine learning can use one common mathematical language, because computers only understand maths, right? And I mean, everything in the world is governed by maths. So once we can convert something into numbers, we can deal with them in a much easier way, be it images, text, audio, any sensor data, or anything, even any customer survey data. So everything becomes mathematically manipulative. So the next time someone says vectors, don't just think of an arrow, think structured numeric representations. That's the machine learning mindset that you will want to have when you learn this subject. So for the next video, as I told you, we'll deal with matrices and why data sets are basically giant structured collections of vectors. Thank you.